So 7.3, 7.4, and 7.5 have some tremendous overlap, but they all three discuss and rotate around these two ideas, one of which is called the reaction quotient, which is notated Q, or the equilibrium constant, which is notated K. Now, before we go too deep into these, let's try to just define them. These are both mathematically derived numbers. Um, the difference between the two is when to use one or the other. Um, K, the equilibrium constant, should only be used when a system is already at equilibrium. So equilibrium has already been established, and you know that to be true. K would be a good time to it'd be a good time to use K. If you're not sure that a system's at equilibrium, or you know for a fact it's not at equilibrium, then you're going to want to use Q. So we'll use Q when we're not at, that was a terrible at sign, not at equilibrium or not sure. And again, these are both just numbers that we're going to mathematically derive here in a moment, but let's just get this out of the way right now. K is at equilibrium, Q is not at equilibrium, or you're just not sure. So let's talk about where these come from. Let me just switch slides here. If you had a reaction, and let's say it's little a, aqueous, plus little b, aqueous, reversible to make little c, aqueous, plus little d, aqueous. The states matter here, and we'll see why in a moment, but um, I want to show you where this idea of Q or K come from. And it doesn't matter which one we're talking about in this context, they're exactly the same. So I'm just going to stick with K for a second. This comes from the rate laws of the forward reaction combined with the rate laws of the reverse reaction. And if you remember, as long as there's only one step, the coefficients become the powers of that rate law. So what ends up happening is this number for K is derived as the concentration of C raised to its coefficient times the concentration of B raised to its coefficient over the concentration of A raised to its coefficient times the concentration of B raised to its coefficient. And just for clarity, these are being multiplied, although you do not have to include the multiplication sign. So at equilibrium, and again, I'm saying I'm at equilibrium because I have a K written here. If I take whatever the heck the concentration of C is and I put it in here and raise it to C's power, and then I take the concentration of D and put it in here and raise it to D's power, and do this for the reactants as well, whatever those concentrations are and whatever they equal out to be here will represent the value of this equilibrium constant K. If you weren't sure if we were at equilibrium or not, we would have just called this a Q. Now, it makes sense that if we're not at equilibrium, the concentrations of these guys are all going to vary. So that means this number will vary, and that's exactly what we're working towards. We're trying to figure out the differences between Q and K and how to interpret them, but for now, we'll just not dwell on it too much. There are two different versions of this equilibrium constant and this reaction quotient constant. Um, a reaction quotient, it's not a constant, but the reaction quotient. And it just depends on whether the substance is an aqueous solution or if it's a gas. So let's rewrite this. We'll do a shorter one. Let's say A, little a, big A, and this is the gas, is reversible, and it can make B, big B, which is also a gas. Now, just as a reminder, when you have brackets here, that means the molar concentration of something, which makes sense. That's how you typically measure the concentration of a solution, is its molarity. Well, how do you measure the concentration of a gas? You do that with partial pressures. So um, instead of the concentrations of these, we're going to use the pressures of these. So the pressure of A raised to its power. Ooh, whoa, my bad, not A. I'm so sorry. Product on top, reactant on bottom. Goodness gracious. the pressure of B raised to B's power over the pressure of A raised to A's power. Now, there is a notation nuance here. Whether you're dealing with K or Q doesn't matter. If you're messing with concentrations, in other words, these are aqueous solutions, then this is going to be labeled as K with a subscript of a C, C for concentration. And if you're talking about pressures, because these are gases, you're just going to label it Kp. There is a mathematical connection between these two. It is on your formula sheet, actually, but it's not going to be asked of you on any exams, including the AP exam. So I wouldn't really worry too much about the connection between these two, but do worry about the notation here. If you're using Kc, you're measuring concentrations. Measuring with Kp, you're measuring pressures. Now, we haven't talked about what would happen if these are solids or liquids, and there's a reason for that. Let's say that A, which is a solid, reaches equilibrium to make B, which is an aqueous solution. Well, if I tried to write out either a reaction quotient Q equals or an equilibrium constant K equals, and again, it doesn't really matter which one, let's just use Q. First of all, I don't see any gases here. I only see an aqueous solution, so this is going to be a QC for concentration. I would take the concentration of B, the molarity of it, raised to its power, which is a 1, over the concentration of A raised to its power, which is a 1. But there's a problem here. The concentration of this guy is just the concentration of a solid. Well, the concentration of a solid or a liquid are both just their densities. And you can't vary the density of a solid or you can't vary the density of a liquid without changing the temperature. And we're not going to do that. So because of that, this guy is just a constant, meaning it's going to be embedded into either Q or K by default. So because of that, you do not include solids or liquids in a Q or K expression. The answer here for this reaction quotient expression is simply QC equals the concentration of B. Again, solids and liquids are not going to appear in any of these expressions. So let's see here. We'll do this one. The decomposition of solid calcium carbonate. So we have CaCO3, which they've told me is a solid, produces calcium oxide, which they've told me is a solid, plus CO2, which I'll turn that to red since I'm writing on this, which is a gas. And they want to write a reaction quotient expression. Well, right off the bat, that's Q. I don't know that I'm at equilibrium. The problem hasn't prompted me to. It told me to write a reaction quotient. And I'm going to look and see, am I dealing with gases or am I dealing with aqueous solutions? Solid, irrelevant, solid, irrelevant. But here I have a gas. So I'm actually solving here for QP and I'm going to use pressures. Again, I look at the products first. This solid is not going to appear in this expression. So the pressure of CO2 raised to the first power, because this balances with all ones here, and then the denominator won't have anything because the only reactant is also a solid. So it's not going to appear in this reaction quotient expression. This would simply be the expression that I'm after here. Let's try another one. Let's do number 5. Write a reaction quotient. So again, that's Q for this guy right here. And I see I'm dealing with aqueous solutions this time. So this is QC. So I'll start with QC equals. Looking at the product first, I see the only product is a solid. So I'm not going to have anything in the numerator except for a 1 because there just has to be something there. So that 1 is understood. The lead 2 plus, PB, make sure you include the 2 plus here or it's not the same thing, times the chloride minus ion. So it's a terrible minus sign. And don't forget to square it because of the 2 coefficient. And this right here would be your reaction quotient expression. Okay? So effectively, that wraps up 7.3, but it doesn't really make much sense to stop there because we've not done anything with this yet. So a useful tool here for this is that this value can be calculated given the conditions you have. So let's say I've got 2Cu2 plus. which is aqueous, plus, let's do a Pb2 plus. And this is going to turn into two Cu1 plus ions. I'm going to run out of room. Here, I'll write it down a little bit. Plus a Pb4 plus aqueous ion. Okay, so let's say that someone's conducting an experiment and they just decide that they're going to take these concentrations of Cu plus, and let's say they just have a bottle of 2 molar of that. And then for the lead 4 plus, Pb4 plus, concentration of that guy is 3 molar. For the Cu2 plus, the concentration is 4 molar. And for the Pb2 plus, the concentration is 5 molar. Okay, so what this experimenter is going to do is they're just going to take these 4 different solutions and really just dump them together. Um, Now, it's not going to be at equilibrium most likely because you've just mixed random amounts of these. Equilibrium is probably going to reestablish itself either to the left or to the right. And that's where we're going with this. But in the meantime, I just want to um, solve for Q. I want to know, because I don't know that I'm at equilibrium, I can't use K, but I want to know what is the actual numerical value of this reaction quotient Q. Well, to do that, we need to first write out that expression. So Q, again, I see an aqueous solution all over, so I will be using QC. QC is going to equal the concentration of the products, Cu2 plus, oh, I'm sorry, Cu1 plus, squared, left off my squared, times the concentration of the lead 4 plus, over the reactants, which is the Cu2 plus, squared, and the Pb2 plus. So this is my reaction quotient expression that I've written out here. Now I just want to know what's the value for Q. Well, I know all of these concentrations right here. So it's just a matter of plugging them into their respective positions. So QC equals the copper 1 plus concentration, which is 2 molar, squared, times the lead 4 plus, which is 3 molar, over the lead or the copper 2 plus, which is 4 molar, and don't forget to square him, and the lead, which is 5 molar, the lead 2 plus, which is 5 molar. When you plug these in, you get a value for Kc of 0.1, oops, let's try that again, 0.15. Now, we still don't have an actual use for this quite yet, but this is the value for it, and now is a great time to go ahead and say there are no units for Q or K. Because these units are completely irrelevant and complicated, it's just commonplace to completely disregard them. So we'll do something with this number here in a moment, but we've solved for it at least. Let's try, we won't actually work this entire problem out, but I do want to show you its usefulness. So on this question, we have a reaction. Let me change colors. We have a reaction here. We know the equilibrium constant, and then they say, given these concentrations at equilibrium, can we find the concentration of C at equilibrium? Okay, well, this all still starts with an equilibrium expression. In this case, it tells us that we're at equilibrium, so this is going to be K instead of Q. I see all of these are aqueous solutions, so this will be Kc. And then we'll just do what we've been doing. The concentration of my product, C, squared because of the coefficient of 2, times the concentration of D, over the concentration of A, squared, times the concentration of B. So this is my equilibrium expression. But this time I'm solving for this guy. Well, let's get the square out of there. I'm solving for the concentration of C. So I'm going to have to do some rearranging here. Well, in order to get C by itself, I'm going to have to multiply by the denominator and divide by the numerator, the part that I don't want, which is the concentration of D. That's going to leave my squared. So after I multiply this side by that, I have to do the same over here. Then I'll have to square root this. So let's go ahead and show this out. This is going to end up equaling I'm going to multiply Kc by the same value in order to get the d's, the a squareds, and the b's to cancel. So that's going to leave me with c squared equals a squared times the concentration of B over the concentration of D times the value of Kc. Now, again, to get rid of the square, I've got to square root both sides. So I'm going to square root this, and I'll square root this, and in order to save myself some room, I'm going to go ahead and just kind of show that here. I've square rooted both sides. The concentration of C is equal to the square root of the concentration of A squared times B divided by the concentration of D times the value of the equilibrium constant Kc. So then it's just a matter of plugging this in. Square root of this guy equals 0.261 squared times 4.13 over 2.91 times the value of the equilibrium constant, which they gave me, 0.0234, which is still inside that square root sign. Okay. And I have lost my calculator apparently, so I will trust you to plug that in. But it's going to be a small value, and it's kind of irrelevant for this moment. But more importantly is realizing what you've done. You've solved for an unknown equilibrium concentration. Whatever this value equals is the concentration of C at equilibrium, which is an important skill as we try to progress through this unit. There's a couple more here. You can pause if you want to try to work on this. These are on your notes, though. So in order to make the most usefulness of this, we need to think about 7.5, which is really honestly a pretty short um, topic, but it's comparing the magnitude of K. Really, K is useful. It's good to know the value of K, but knowing the magnitude of K, whether it's large, small, however that falls, is almost just as useful. So in order to help us do this, I want to think about a really simple reaction. Let's just say it's A, which is aqueous, turning into B, which is aqueous. If I were going to write my equilibrium expression here, K, again, aqueous, aqueous, so I know I'm using Kc, would equal the concentration of B over the concentration of A. So there's a couple options that can happen here for K, um, but we have to kind of bust up a misconception first. Just because something is at equilibrium does not mean that there's an equal amount of A and an equal amount of B. In fact, that's almost never true. The idea of equilibrium is that the rate at which A is turning into B is exactly the same as the rate at which B is turning into A. So it appears that their concentrations are not changing. Well, their concentrations aren't changing, but it appears that nothing's happening. But there's still a reaction taking place. A is turning into B, B is turning into A, but it's happening at the same rate. So it appears to the macroscopic world and the concentration changes that nothing is happening. But that does not mean that this amount of B and this amount of A are equal. But let's pretend for a moment that we found that K does equal 1. Well, the only way, because this K right here is this Kc, the only way this can be 1 is if this numerator and this denominator are the same value. That's the only way to get a fraction that's 1. In this perfect case, that would mean that the left side, the reactant side, and the product side are equally favored. In other words, the concentration of A at equilibrium and the concentration of B at equilibrium are equal. So the concentration of A and the concentration of B at equilibrium are equal. This means that this is neither reactant nor product favored. And what I mean by reactant or product favored is this equilibrium isn't leaning towards one side. Sometimes equilibriums might make way more product than they do reactant, or way more reactant than they do product. In this case, when K is 1, that's not true. Neither forward nor reverse, nor reactant nor product is favored. Well, if K can equal 1, then it makes sense to think that K should be able to be greater than 1, or K should be able to be less than 1. Well, think about the fraction here. If I need K to be greater than 1, that means this numerator, the product, has to have a larger concentration than the reactant A. So here, the concentration of A is going to be greater than the concentration of B at equal, whoa, I wrote that so backwards. My apologies. Let me try that again. The concentration of B is going to be greater than the concentration of A at equilibrium. Well, we can say this by saying this is a product-favored process. This equilibrium, when it's established, is leaning more towards the product side. You're going to end up seeing more B than you have of A. Well, the opposite's true down here. If K is going to be less than 1, the only way for that to happen is for there to be less numerator, which is the product, than there is denominator, which is the reactant. So in this case, that's what I was trying to write a second ago, the concentration of A is going to be greater than the concentration of B at equilibrium. And we can say that this is reactant favored. There's going to be more reactant at equilibrium than product. This reaction really didn't push very hard this way. It more favored staying this direction. Okay? So there's two more things that can happen. It's a little uncomfortable at first to think about, but we notate it with two greater than signs. What this means is that K is significantly greater than 1. You have a large value of K. There's not a fast or hard rule here. A good rule of thumb, though, is 1,000. If K is greater than 1,000, we can say that this is extremely product favored. That means that basically all of A is turning into B. This is very product favored. So another way of saying that is that this essentially goes to completion. Okay, so this is essentially going to completion. Now that's handy, but before we get there, we have to realize something. This can't actually go to completion. Since this process is reversible, if I were to use up all of the A, some of this B will have to turn back into A. So the reaction can't literally go to completion, but for all intents and purposes, it basically does. That's useful because if we can assume that all of this turns into B, we can just use stoichiometry in order to find this out, because that's no different than a limiting reactant. The reaction progresses until you run out of limiting reactant. This reaction is going to progress until basically you're out of A, but it's critical you understand you never actually run out of A, because equilibrium means there has to be some reactant and some product. Well, the other direction of this is that K is significantly less than 1. This means that the reaction essentially does not progress. The reaction essentially doesn't occur, meaning it's almost all A at equilibrium. Hardly any turns into B, but again, we know there has to be some that turns into B, otherwise it can't be at equilibrium. There must be some reactant and some product remaining, or it can't be at equilibrium. This is going to create a helpful trick later in this unit, but it's just easier to realize the reaction essentially doesn't change or doesn't occur, which means if we think about it, the concentration of A, my reactant, basically won't change there. So let's look at this we-do problem here. We have 2A plus a B making 2C, and they give me the K value, which is something times 10 to the negative fourth. So this is the first thing I'm going to look at and realize this K is certainly less than 1. In fact, it's 10 to the negative fourth. So this is tiny as I write it in giant screaming letters, meaning this is extremely reactant favored. I would expect there to be hardly any product made in this process. It's also worth noting we start with the same amount of A as we do B. Now it's asking what would be true of the partial pressures of these gases at equilibrium. Well, I'm going to start with C. This K is tiny. This reaction, once it hits equilibrium, is basically going to make no C whatsoever. So C has to be by far the smallest of the pressures of A, B, or C. So this idea of A equaling B equaling C is crazy. This one right here, A and B, are both saying that C is significantly greater than A or B, but that's backwards. C needs to be significantly less than either A or B. So this comes down to, well, who's got the larger pressure here now, A or B? And this all comes down to their coefficients. For every two A that go away, only one B is going away. So even though almost none of this B is going away, however much of it does go away, there's going to be twice as much A that goes away. So no matter what, the concentration of A has to be, or in this case, the pressure of A has to be less than the pressure of B, which means this answer must be C. Okay, we can do one more. I want to pick this one right here. We have A plus B is reversible to make C plus 2D. And I see my K value. That's where my eyes are always going to go first. This is huge. This has a huge value of K, meaning this equilibrium is seriously favoring these products here. I would expect there to be a significant amount of C and D. But the first one, it tells us there's 5 moles of A and 5 moles of B, so they're equal when we start. It wants to know what's true when we compare A to B here when it hits equilibrium. Well, for every one A that goes away, one B is going away. So we're going to have the same amount at equilibrium. That amount will be almost nothing. Not quite nothing, but almost nothing. And they have to be equal because their coefficients were equal. And we started with 5 moles of each. This next batch asks us to compare C to D. Almost all of this is going to turn into C and D. So C and D are going to have large concentrations, but D's got that coefficient of 2. So there's going to be 2 D's for every 1 C. That means D is going to be larger. This one asks us to compare A to C. Well, we already have established that A is basically going to be gone. There will be almost none of it because it all almost got converted to C. So A must, whoop, that's wrong. C must be greater than A. And then lastly, we're comparing A to D. That's going to be the exact same scenario. I don't even care about the coefficients here. Almost every single bit of this A has disappeared. So A is going to be less than D, or D is going to be greater than A.